Welcome back. For 6 episodes, we have been solving first-order differential equations, separable, linear, exact, Bernoulli, always assuming that a solution exists and that the one we find is the only one. Today we stop assuming and start guaranteeing. The first half of this episode is the existence and uniqueness theorem, a result that tells you, before you write down a single integral, whether your initial value problem has a solution at all, and whether that solution is the only curve through your starting point. We will also look at the equations that break the rules, solutions that split into infinitely many, and solutions that race off to infinity in finite time. The second half introduces a special family, the autonomous equations, where the rate of change depends only on the state. These hide a gorgeous one-dimensional picture, the phase line, that reveals the destiny of every solution without any formula. And our showcase will be the logistic equation, the most famous model of growth with a ceiling. Let us frame the problem precisely. A first-order initial value problem has 2 parts, the differential equation, y prime equals f of x comma y, and an initial condition, y of x naught equals y naught. Think back to slope fields from episode 2. The differential equation assigns a slope to every point in the plane, a little dash showing which way a solution must head as it passes through. A solution is a curve that always flows along those dashes. The initial condition pins that curve to one specific point, x naught comma y naught. Now 2 questions arise that we have quietly ignored. First, existence. Is there any solution curve at all through that point? Second, uniqueness. Is there exactly one such curve, or might several different solutions all pass through the same starting point? Geometrically, could 2 solution curves cross? These sound like technicalities, but the answers shape everything. If solutions could branch, the future would not be determined by the present, and most of physics would be in trouble. Here is the theorem, named for the mathematicians Picard and Lindelöf. Take the initial value problem y prime equals f of x comma y with y of x naught equals y naught. Suppose that on some rectangle in the plane containing your starting point, 2 things are continuous, the function f itself and the partial derivative of f with respect to y. Then there is some interval around x naught on which the problem has exactly one solution. Read it in 3 parts. First, continuity of f alone is enough to guarantee that at least one solution exists. Second, adding continuity of the partial derivative with respect to y upgrades that to uniqueness. Exactly one solution, no branching. Intuitively, that partial derivative controls how fast nearby solution curves can spread apart. Keeping it bounded stops 2 curves from ever splitting out of a single point. Third, and this is crucial, the conclusion is local. It promises a solution only on some interval around the start, possibly a short one. The theorem never promises the solution lasts forever. We will see exactly why that caution is necessary. Let us watch uniqueness break. Consider y prime equals the cube root of y, with y of 0 equal to 0. The right-hand side, the cube root of y, is continuous everywhere, so the theorem promises a solution exists. But now compute the partial derivative with respect to y. By the power rule, it is 1/3 times y to the negative 2/3, and as y approaches 0, that expression blows up to infinity. So the uniqueness hypothesis fails right at our starting point, the origin. And the consequence is dramatic. One obvious solution is the constant 0. Y identically equal to 0 satisfies the equation, since the cube root of 0 is 0. But here is a second, y equals the quantity 2/3 x raised to the 3/2 power. You can check it satisfies both the equation and the initial condition. In fact, a solution can sit at 0 for any amount of time and then peel away along that curve, which gives infinitely many distinct solutions through the single point. The future is not determined by the present. That is exactly the pathology uniqueness is meant to forbid, and it appears precisely where the partial derivative misbehaves. Now the opposite warning. A solution can be perfectly unique and still fail to exist for long. Take y prime equals y squared with y of 0 equal to 1. Both f, which is y squared, and its partial derivative, which is 2y, are continuous everywhere, so the theorem hands us existence and uniqueness. Let us actually solve it. It is separable. Move the y squared over and integrate. The integral of 1 over y squared dy equals the integral of dx. The left side gives negative 1 over y. The right side gives x plus a constant. Apply the initial condition, y of 0 equals 1, and the constant comes out to negative 1. Solving for y, we get y equals 1 over the quantity 1 minus x. Now look at what happens as x approaches 1 from below. The denominator goes to 0 and y rockets to infinity. The solution exists only on the interval from negative infinity up to 1. It blows up in finite time, even though the equation looked tame and the theorem fully applied. This is the deep reason the existence guarantee is only local. A smooth equation makes no promise about how long its solution survives. Now we specialize to a particularly elegant family. An equation is called autonomous when the right-hand side depends only on y, not on the independent variable. We write it y prime equals f of y. The clock, whether we call it x or t, does not appear explicitly. The rate of change depends only on the current state, never on what time it is. Autonomous equations have lovely properties. They are always separable, so in principle you can integrate 1 over f of y. More importantly, they are time translation invariant. If some curve solves the equation, then sliding that whole curve left or right in time gives another solution. The dynamics do not care when you start the clock. Geometrically, this means the slope field looks identical in every vertical strip. The slope at a point depends only on the height y, not on the horizontal position. And that single fact is the key that unlocks the next idea. Because the behavior depends only on y, we can collapse the entire two-dimensional slope field down onto a single vertical axis and read off everything we need. Here is the payoff. Because an autonomous equation depends only on y, we can analyze it on a single vertical line called the phase line. First, find the equilibrium solutions, also called critical points. These are the constant values c, where f of c equals 0. At such a value, y prime is 0, so a solution starting there never moves. It sits at that height forever. Now draw the y-axis and mark every root of f on it. Between consecutive roots, the function f keeps one sign because it can only change sign by passing through a root. Wherever f of y is positive, y prime is positive, so y is increasing. Draw an arrow pointing up. Wherever f of y is negative, y is decreasing. Draw an arrow pointing down. That is the entire phase line, a vertical axis, dots at the equilibria, and arrows between them. And it tells you the long-term fate of every solution. Start anywhere, follow the arrow, and you flow toward or away from the equilibria. We extracted the complete qualitative behavior without solving a single integral. That is the power of thinking geometrically. The phase line does more than show flow, it classifies each equilibrium by its stability. Look at the two arrows on either side of an equilibrium point. If both arrows point toward the equilibrium, up from below and down from above, then nearby solutions converge to it. We call this a stable equilibrium, or a sink, it attracts. If both arrows point away, down below and up above, nearby solutions flee from it, and we call it unstable, or a source, it repels. There is a third case. If the arrows point the same direction on both sides, say up below and up above, then the equilibrium attracts from one side and repels from the other. That is a semi-stable equilibrium. There is also a quick algebraic test. Evaluate the derivative of f at the equilibrium. If f prime of c is negative, the equilibrium is stable. If f prime of c is positive, it is unstable. And if f prime of c is 0, the test is inconclusive and you fall back on the phase line itself. Stable, unstable, semi-stable. 3 words that summarize the destiny of every solution near each equilibrium. Let us connect the phase line back to the real solution curves in the xy plane, because the link is what makes the whole picture trustworthy. Each equilibrium becomes a horizontal line, a constant solution that runs flat forever. Between two equilibria, the derivative keeps one sign, so a solution can only rise or only fall. It is monotone, never wiggling up and down. Crucially, a solution curve can never cross an equilibrium line. That follows from the uniqueness theorem from the first half of the episode. If a curve touched the constant solution, two different solutions would share a point, which uniqueness forbids. So instead of crossing, a solution can only approach an equilibrium asymptotically, flattening toward it without ever arriving. And since each solution is both bounded by the neighboring equilibria and monotone, it must settle onto one of them as time runs forward or backward. In short, the phase line is nothing but the family of solution curves seen edge-on, looking straight down the time axis. Existence uniqueness from the first half and the phase line from the second half are the same story told twice. Here is the phase line we will care about most, drawn for the logistic equation we are about to meet. There are two equilibria. At the bottom, where y equals 0, is an unstable source. The arrows on both sides point away from it. At the top, where y equals capital K, is a stable sink. The arrows on both sides point toward it. In the region between 0 and k, the arrow points up, meaning any population starting in that band grows. Above k, the arrow points down, meaning a population that overshoots its ceiling falls back. And below 0, biologically meaningless but mathematically real, the arrow points down. Read the consequence straight off the picture. No matter where a positive population starts, small or large, it flows toward the value k. That k is the carrying capacity, the natural ceiling of the system. Notice we have described the entire long-term behavior of every solution without writing down a formula. 3 regions, 2 dots, a handful of arrows. The whole story of logistic growth lives on this single vertical line. Now the headline example, the logistic equation. Pure exponential growth, y prime equals ry, predicts a population doubling forever, clearly unrealistic, since no environment has infinite food or space. The logistic model fixes this by multiplying the growth rate by a breaking factor. We write y prime equals r times y times the quantity 1 minus y over k. Here r is the intrinsic growth rate and capital K is the carrying capacity. the maximum population the environment can sustain. Look at how it behaves. When y is small, the factor 1 minus y over k is close to 1, so the equation is approximately y prime equals ry, nearly exponential, explosive early growth. But as y climbs toward k, that breaking factor shrinks toward 0 and growth grinds to a halt. The equilibria are exactly where the right side vanishes, at y equals 0 and at y equals k. Checking the derivative test, f prime at 0 is r, which is positive, so 0 is unstable. F prime at k is negative r, which is negative, so k is stable. Exactly the phase line we just drew. Let us actually solve the logistic equation to confirm what the phase line predicted. The equation is separable. Move everything in y to one side and integrate. The integral of 1 over y times the quantity 1 minus y over k dy equals the integral of r dx. The left side needs partial fractions. It splits into 1 over y plus a second piece, 1 over k divided by 1 minus y over k. Integrate both pieces, each gives a logarithm, then combine, take the exponential, and solve for y. The result is the famous logistic curve y equals k over the quantity 1 plus a times e to the negative rx, where the constant a equals k minus y naught, all over y naught set by the initial population. Now read the limits. As x goes to infinity, e to the negative rx decays to 0, the denominator becomes 1, and y approaches k, the stable carrying capacity, exactly as the phase line promised. Going backward, as x goes to negative infinity, y approaches 0. The graph rises slowly, then steeply through the middle, then levels off. The classic S shape, also called a sigmoid. Formula and phase line agree perfectly. Here is that S-shaped curve in full. Time runs along the horizontal axis and the population along the vertical. The dashed horizontal line is the carrying capacity, the value k. Look at the family of curves. A population starting small, well below k, rises slowly at first, then accelerates through a steep middle stretch, then eases off and levels out just under k, the signature S shape. The steepest point, where growth is fastest, occurs exactly at half the carrying capacity, the inflection point. A population that happens to start above k, perhaps after a temporary surplus, simply decays back down to k from above. And the flat line along the bottom, at y equals 0, is the unstable equilibrium. A population of exactly 0 stays 0, but the slightest positive nudge sends it climbing toward k. Every curve in this picture is consistent with the phase line we drew earlier. The arrows there become the rising and falling trends here. The phase line told us the destination. This graph shows the journey. One more example, this time purely qualitative. No formula, just the phase line. Take y prime equals f of y, where f of y is y times the quantity 1 minus y times the quantity 2 minus y. The equilibria are where the product is 0, y equals 0, y equals 1, and y equals 2. Now test the sign of f in each region by plugging in a sample point. For y less than 0, all three factors combine to give a positive value, so the arrow points up. For y between 0 and 1, f is negative, arrow down. For y between 1 and 2, f is positive again, arrow up. And for y above 2, f is negative, arrow down. Now classify. At y equals 0, the arrow points up from below and down from above, both toward it, so it is stable. At y equals 1, arrows point away on both sides, so it is unstable. At y equals 2, arrows point toward it from both sides, so it is stable. Stable, unstable, stable, alternating up the line. Notice the pattern, equilibria, alternate instability, which is exactly what you expect when f changes sign cleanly at each simple root. A little history rounds out the episode. The existence and uniqueness theory grew from the work of Émile Picard in the 1890s. His idea was beautiful and constructive. Rewrite the differential equation as an integral equation, then build the solution by successive approximations. Start with a guess, plug it in, integrate to get a better guess, and repeat. The sequence converges to the true solution. This is now called Picard iteration, and it proves not just that a solution exists, but actually manufactures it. The Finnish mathematician Ernst Lindelöf sharpened the conditions, which is why the theorem carries both their names. As for the logistic equation, it was introduced by the Belgian mathematician Pierre-François Verhulst in 1838. He was reacting to Malthus, who had predicted unbounded exponential population growth. Verhulst added the ceiling. His work was largely forgotten, then rediscovered in the 1920s by Pearl and Reed, and today the logistic curve is everywhere, modeling epidemics, the adoption of new technology, and even the activation functions inside neural networks. Let us recap. The existence and uniqueness theorem, Picard Lindelöf, says that if f and its partial derivative with respect to y are continuous near your starting point, then the initial value problem has exactly one solution, at least locally. Continuity of f gives existence, continuity of the partial derivative gives uniqueness. We saw both failures. Y prime equals the cube root of y branches into infinitely many solutions because the partial derivative blows up, and y prime equals y squared races to infinity in finite time even though it is perfectly smooth, which is why existence is only local. Then, autonomous equations, y prime equals f of y, where the rate depends only on the state. Their tool is the phase line. Mark the equilibria where f equals 0, draw arrows up where f is positive and down where f is negative, and read off stability. Stable sinks, unstable sources, and semi-stable points in between, or just test the sign of f prime at each equilibrium. The logistic equation tied it together, with 0 unstable, k stable, and the S-shaped solution curve flowing to the carrying capacity. Next episode, we leave first-order equations and build the structural theory of second-order linear equations. Today, we ask the questions we had been taking for granted. Does a solution exist, and is it unique? The existence and uniqueness theorem, also called the Picard Lindelöf theorem, gives the guarantee. If you write the equation as y prime equals f of x comma y, and if f is continuous near your starting point and its partial derivative with respect to y is also continuous there, then through that point passes exactly one solution curve, at least on some small interval around the start. Continuity of f alone buys you existence. Continuity of the partial derivative buys you uniqueness on top of it. We saw both failures. When f has an infinite slope in y, like the cube root example, uniqueness breaks and infinitely many solutions branch from one point. And even a perfectly smooth equation like y prime equals y squared can have its solution blow up to infinity in finite time, so existence is only ever local. Then we studied autonomous equations, y prime equals f of y, where the rate depends only on the state. Their secret is the phase line. Mark the values of y where f of y equals 0, the equilibrium solutions, and between them draw an arrow up where f is positive and down where f is negative. That single vertical picture classifies every equilibrium as stable, unstable, or semi-stable, and tells you the fate of every solution without solving a thing. Our headline example was the logistic equation, y prime equals r times y times the quantity 1 minus y over k, whose stable carrying capacity k and unstable 0 produce the famous S-shaped growth curve. Next episode, we step up to second-order linear equations and the structure of their solutions. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.